Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology. We have been learning the subject basic electrical engineering where so far we learn in the single phase AC circuit where we learn about the characteristics of different components resistance, inductor, capacitor individually and in the combination of resistance and inductor, combination of resistance and capacitor and combination of resistance, inductor and capacitor in series, and we have applied AC signal. By that way we found the characteristics of individual resistance, inductor, capacitor and the combination of RL, RC and RLC. Right, what we found that it is not that much simple when you apply the DC signal where how the RLC are performing. Same way here when you apply AC signal how the RLC are performing. Right, now before that we learned about how you can generate a single phase AC signal. Right, same way in our today's session we are going to learn about the three phase AC signals. In another sense we have to learn about three phase AC circuits. Right, so if we talk about this three phase AC circuit, again our basic components are R, L and C. Right, so again here with the RLC this combination we are going to apply a AC signal. Right, before that I need to generate three phase AC signal. So we have learned in a generation of single phase AC circuit where there are two magnets and in between the two magnets we put the conductor. With the conductor is rotating in anti-clockwise direction, so created static magnetic field and dynamic magnetic field. Right, so here the combination of static magnetic field and dynamic magnetic field that will generate EMF as per the Faraday's law of electromagnetic induction. Now same terminology we have to again discuss, but instead of single phase now we are talking in terms of the three phase. Now within a same assembly of single phase we can generate two more individual phases, we can generate a three phase AC signal. Now this is easily achievable where within a same assembly if we put more two conductors, by that way we can generate two more separate AC signal along with the first one. So by that way you can generate a three phase AC signal and this is much cost effective. So we'll one by one discuss, and during this phase of a three phase AC circuit we have to first discuss about the introduction of three phase AC circuits. Then we are going to discuss about the one of the type of three phase AC circuit which is called a star connection. Another type we can discuss about the delta connection, and then power measurement of this three phase circuit throughout this discussion. Right, so our today's session we are specifically concentrate on the three phase AC signal. Right, so it's nothing but a generation of three phase AC signal. Let's say how it's going to be generated. Right, so you can see here we'll first start with the introduction of three phase AC signal where all electric power is generated and distributed in three phases. Now why this is very important, because with three AC signals, right, so here it would be much cost effective rather than you generate only a single phase AC circuit and you apply to the or you distribute to the load. Right, so one phase, two phase or more than three phase input can be taken from three phase system rather than generated independently. Right, so here you can see high power motors prefer a steady torque, especially one created a rotating magnetic field, and the three phase system is more economical than a single phase. Right, so within a same assembly if you can be able to generate a three phase which is more cost effective in that sense here within a same assembly, so you can generate, you can save the cost of copper as a conductor, aluminum as a conductor. So by that way the system is more economical. Right, so one by one if we discuss about the generation of three phase, you can see here can be present or must be present in order to produce a electrical element. One is called a magnetic field, conductor and relative motion. Right, so here magnetic field that will generate two kinds of magnetic field. One magnetic field is created by a magnet. You can see these magnets are a fixed magnet, they are static. Right, fixed, that's why this will create static magnetic field. Right, and inside you can see there are now three conductors. One conductor story, you already know about the generation of single phase AC signal, where one conductor is moving in anti-clockwise direction. Since this is in a motion, that will create a dynamic magnetic field, right? So here, instead of one conductor, now I am putting extra two more conductors, which is 120-degree apart with each other, right? By that way, this inside this two magnet, this gap, you can see there are three conductors and all are placed 120-degree apart with each other, and all are rotating in the anti-clockwise direction, where there is nothing but the three vectors which are moving in a anti-clockwise direction with the angular velocity of omega, and these are 120-degree apart with each other. So this will generate dynamic magnetic field. So here what I have done during this process, I have used the combination of static magnetic field and dynamic magnetic field. Once you combine these two, there is a generation of AC signal. So you can see from this diagram, where there are three coils are moving in anti-clockwise direction and apart with 120-degree each other. Once it's coming to the contact of the conductor, see the generation of AC signal through this spotted line. So here this principle is based on the electromagnetic induction of Faraday's law, where conductor cuts the line of magnetic flux and the voltage induced in the conductor, right? So between two magnets there is a generation of magnetic flux, and once the conductors are moving in an anti-clockwise direction, that will cut the magnetic flux, that is the d phi by dt, and there is a induction of EMF E is equal to minus d phi by dt. If there are n number of turns, it value is E, the induced EMF E is equal to minus n into d phi by dt. This is nothing but the electromagnetic induction, Faraday's law, right? So here direction and speed are very important, since this is a vector quantity, right? So here further you can see this that will create a magnet, and it is moving in anti-clockwise direction. So by this way, in three phase AC signal, three coils are fastened tightly together and displaced from each other with the 120-degree, right? So here all these three conductors are moving in the anti-clockwise direction with the angle of 120-degree exactly, right? So by that way, this will generate three separate phases of AC, right, of alternating signal. So it is made to rotate about a fixed axis and uniform in a uniform magnetic field. So from this you can be able to see an EMF is induced in each coil with a phase difference of 120 degrees. So here I am taking now the label of conductors, like one of the conductor is A1, A2, another conductor is B1, B2, and third conductor is C1, C2, and all these three conductors are separated by 120 degree with each other. So our we'll always start with the reference of conductor A1 and A2, right? So you can see here in this particular diagram, where there are two magnets, and this two magnet will create a static magnetic field inside the gap between two magnets. Here the magnetic flux is being induced, and where I am going to put the three conductors A1, A2, B1, B2, and C1, C2 with a 120 degree apart with each other, and all are moving in anti-clockwise direction with the same speed, with the same angular velocity of omega, right? So once it start moving in anti-clockwise direction, you can see here, you can see the steps of 30 angle of each conductor and how they are going to generate AC signal based on the Faraday's law, right? So let's say the conductor A1 and A2 that will start with the angle 0, right? You can see in a vector representation later on, but one conductor A1 and A2 which is moving in anti-clockwise direction and start the position at the 0. So that particular signal I can consider E of A1 A2 is equal to E0 sine omega t, because it starts with the angle 0, right? The another vector which is 120 degree apart from the A1 and A2, that conductor I define as B1 and B2, right? So that will generate the same signal, identical signal like A1 and A2, right? But it is a 120 degree apart. So that starts after the 120 degree of E1 and A2. So that I define as, here you can see that I define as EB1 B2 is equal to E0 sine omega t minus 120, right? So here you can see the gap where B1 B2 is a 120 degree lagging by A1 and A2, and the third conductor I define as a C1 and C2 which is 240 degree from the reference A1 and A2, and from B1 and B2 is 120 degree. So if you take the reference of conductor A1 and A2, then C1 and C2 is a 240 degree lagging by the reference angle 0. So you can see here the third conductor C1 and C2 that will also induced EMF within a same assembly but which is 120 degree later. So that value I define, you can see here every steps of 30 angle how the generation of AC signal is possible through these three individual conductors, right? So one by one you can see the equation behind this generation of EMF of this individual three phases you can see within a same assembly. Then we just now discussed at E of A1 and A2 is equal to E0 sine omega t, you can consider as E0 sine omega t minus 0. So that means this vector or this conductor starts at angle 0 between these two magnets, you can see here. Same way here the conductor B1 and B2, it starts at angle 120 degrees. So I can consider the generation of EMF from this conductor E of B1 and B2 is equal to E0 sine omega t minus 120, right? So the vector number 3 which is or conductor 3 which is C1 and C2. So E C1 of C1 and C2 is equal to E0 sine omega t minus 4 pi divided by 3. In another sense, this is called E0 into sine omega t minus 240, right? So here these three vectors are moving in anti-clockwise direction with the angle or with the phase difference of 120, exactly 120 degree with each other, right? So by that way you can see here E0 is nothing but the peak value of induced EMF, omega is nothing but the angular velocity of the coil, and time t is defined as this small time t, where you can see this the phase sequence of and vector representation of this three phase induced EMF, right? So in generally if I am going to define this all these three vectors or all these three conductors which will induce AC signal as A1 A2 B1 B2 C1 C2, right? Instead of that, for I have taken a standardized manner which one phase I define as a red phase which is generated by conductor A1 and A2. Another I have defined as a yellow phase which is nothing but the generated AC signal through B1 and B2 conductor, and the third I can consider as a blue phase which is nothing but the AC signal generated by the conductor C1 and C2. So all this phenomena if I am taking all together, you can see this here. This is the vector representation or vector diagram or phasor diagram of this three phase AC signal, where you can see the first vector start at angle 0 which is a red vector or which is a red phase. Second phase is nothing but the yellow phase, it start at angle 120 degree, and the third phase blue phase which start at the angle 240 from the first one, right? So from this vector diagram you can see all these three vectors are 120 degree apart with each other, and all these vectors are moving in a anti-clockwise direction between two magnets, you can imagine like this way, right? So based on that, now we'll follow a generalized mathematical equation based on this three phase AC signal. First I define now, instead of A1 A2 I define this phase as a red phase. So now my mathematical equation would be ER is equal to E0 sine omega t. In another sense, that is equal to E0 sine omega t minus or plus angle 0, right? Same way the yellow phase EY, instead of E of B1 and B2, so EY is equal to E0 sine omega t minus 2 pi by 3, that is equal to E0 sine omega t minus angle 120. Same way here EB, instead of E of C1 and C2, that is equal to E0 sine omega t minus 4 pi divided by 3, and that is equal to E0 sine omega t minus 240, right? So this is nothing but the generation of three phase in standardized way, and in our real practical life we are using the same three phase in all the applications, all industrial application as well as the residential application. From this you can be able to see the waveforms of this three phase induced in EMF, where these are the mathematical equation, and based on this mathematical equation if you find the waveform, you can see here the red phase starts at the angle 0, right, and the yellow phase will start at the angle 120 as per the mathematical equation, and the third equation you have defined this EB is equal to E0 sin omega t minus 240. So here the blue phase starts at angle 240, right. So by that way, see, within a same assembly you can be able to generate three phases, right. That means here the efficiency is 3 times more than that of what we have discussed in a single phase, right. So almost in all the application, if you see the in a power plant, there is a generation of three phase or there is a generation of polyphase AC signal. If there is a generation of polyphase AC signal, then the cost of generation is very less, that is very economy, and then we can afford it, right. So this is what the generation of AC signal says. So within a same assembly, if you just put two more conductors which is 120 degree apart with each other, then that process is much easy to generate here the three phase AC signal, right. So thank you dear students. If you have any doubt, you can write in a comment box. Thank you very much.